So I'm happy to say we still have so many people here because this will be a very hard session because quantum computing is hard. So myself was a computational biologist, bioinformatician, and then a data scientist. I did sequence analysis, next generation sequence analysis, and computational biology. I did modeling, Monte Carlo simulation modeling, molecular dynamics, and design optimization algorithm, and machine learning algorithm. But when I was put in this position to be a program officer to manage our quantum computing programs, it still took me a hard time to learn. So it is a hard topic. So I'm glad we still have so many people. And so if we want to keep United States at the leading position of technology, there's two areas we must heavily invest. One is artificial intelligence, another one is quantum computing. So we already say artificial intelligence already makes significant impact. It's changing the world, the whole world. So quantum computing, we don't know. There's a lot of uncertainty here. So let's say. So since quantum computing is a pretty hard topic, so I want to start. I know many of people come to this conference with background of bioinformatician or computational biology. So I want to simply talk about what is quantum computing. So quantum computing uses the uncertainty of quantum mechanics. So when you go to quantum mechanics, there's a lot of uncertainties here. For example, the status of electron. It could be in base status or in exacting status. And in quantum mechanics, there is a probability. What is the percentage to be in base percentage in the exactment status? So quantum computing make use of the uncertainty. So one status is could be in like base status, or could be also be in exactment status. So that is the uncertainty of quantum mechanics, and quantum computing is going to use that. So in quantum computing, one status could have 0 or 1 combination. But in classic, so you could only have 0 or 1. So that is a significant difference of two different computing. And in classical computer, so when you do calculation, you do one operation for each frequency, clock frequency. You do one of that. But in quantum computer, because there is something called entanglement, entanglement means you can connect multiple quantum bits together. When you do operation in one of that, all the other entangled qubit will be changed. So this will significantly increase the speed of the calculation. And so because of entanglement, because of the operation can be exponentially increased, so the speed of quantum computing could be exponential. And unfortunately, because of uncertainty, so quantum computing could have errors. So for the use cases, so for classical computer, so we're already using our classical computer in a lot of like office, web browsing, and scientific computing as well, like AI. So classical computer can do a lot of work, even for very hard problems. But there are some problems beyond the capability of quantum computing. We will see that. So as you can see, there is a problem space. So if you have been in a mathematical optimization operation research area, you will know what is optimization. So the problem space can be classified as can be resolved in polynomial time, or no, there's no polynomial algorithm to resolve. So that's basically people say. But there is some space in the middle which can be resolved by quantum computing. That space is very, very hard for classical computing. And as you can see, so the computing time will increase significantly when you use classical computer for some problems. So here is some typical examples using quantum computer. So since we don't have a real quantum computer, we don't have a real production level quantum computer right now. So you are not saying this algorithm has been widely adopted. But we don't know, maybe in 5 years or 10 years, we have a production level quantum computer. You will see those algorithms will make significant difference in the computational world. The first one is called Shor's algorithm. This is one of the most old algorithms is to be decrypt the password. So because of this algorithm, even we don't have a real quantum computer list in United States, it's called for quantum proof algorithm to ensure current encryption of the password cannot be decrypted by quantum computing in the future. So last year, they called that such algorithm, and they received like more than 80 submissions, and eventually they selected 3. So I already say the deployment of those algorithms from industry. They are implementing those algorithms, trying to deploy to the real applications. Even we don't have one, but it could be decrypted in the future. And the second one is called graph algorithm. It's a search algorithm. So you search for unstructured data or unsorted data. So for unsorted data, so if you want to search, basically you have to go through all of them. But so in classical computer, but in quantum computer, the search time will be significantly decreased. And quantum computer can also be used to resolve quantum chemistry. If you have been working in quantum chemistry, the computation requirement is very, very high. So quantum computer can be used as a simulator to resolve quantum chemistry problems. And the first example I showed is an algorithm called QUBO. This one has been widely adopted in industry. And because we have a quantum simulator, some people call it quantum annealer, which it's not a real quantum computer. It can only be used to resolve a few very specific mathematical problems. QUBO is one of that. And a lot of industry optimization problem can be formulated as a QUBO. I think it means quadratic unconstrained binary optimization. This is a very hard problem, but if you use D-wave quantum computer, which have 5,000 qubits, can resolve a lot of those. And the last one is an example I learned a few years ago. It is a real application. It actually uses QUBO algorithm to filter drug design, filter ligand in drug design. So recently, industry, IBM just released their, I think it's quantum computer, more than 1,000 qubits about 2 years ago. And they also deployed the quantum system too. And Google, last year, they deployed quantum chips with 105 qubits. This is significantly lower in IBM, but the advantage is fault tolerance, because your quantum computer has errors. This one has significantly lower errors. And D-Wave, as I just mentioned, they have a lot of industry applications with their quantum annealer, and other companies. I don't want to mention all of them. They are all very interested. Microsoft, Google, NVIDIA, they are all trying to invest heavily in quantum computing. So in government, in the United States, we have this act called National Quantum Initiative Act. This one was published in 2018. And this one is trying to push the United States to accelerate development of quantum computing technology, quantum science, information science technology. And Department of Energy, as you can see, significantly investment in quantum computing. And NIH has 2 very significant investment in quantum computing. And at least they call the algorithm, the decryption, quantum proof encryption algorithm. And within NIH, in 2023, Congress required our office to launch a pilot with Department of Energy to study the potential of quantum computing in biomedical science. And in 2023, our office sponsored with Department of Energy co-sponsored the study, this roundtable, and I will talk more about that. And last year, our office and the NCI, the Cancer Institute, co-sponsored the Quantum Computing Innovation Lab. And this year, right now, we have an Quantum Computing Challenge. So our office contributed about half of the funding, and it's led by NCATS. So as you can see, the quantum computing roundtable is led by Dr. Chandra McWhinney from Oregon Health Science University, and Talita from Lawrence Berkeley National Lab. So those are the two quantum computing leaders within the United States, and they published a report about quantum computing. And they identified 3 areas which quantum computing could make significant progress, impact in those 3. The first one is biomedical image and diagnostics. The second one is biological sequence analysis and processing. The third one is drug design. Those are specific to biomedical research area, and they also identified 5 technical areas, which are not specific to biomedical area, but is general for all the quantum computing progress. So, and the second activity we sponsored is this Quantum Innovation Lab. So the first 2 people is my previous colleagues. So Dr. Nora Bevan, she was my supervisor. So currently she is the Chief Data Officer in Jefferson Lab, he's still in lab. And my other colleague is Chris Seavey. So he is currently a computational scientist in NCI, and myself and 3, and Jennifer Koch, Samantha Finstead, and Tony DeKerber. They are my NCI colleagues. They organized this innovation lab with me. So this happened last December. So we had 82 applicants. We selected 26 according to their background and their expertise. And we have a company is facilitated the innovation lab. They are very experienced. And we also invited 5 mentors and 3 program officers and 1 provocators. Actually, the provocator is Dr. Shannon McWhinney. And so we found a place in Oregon, mountain, somewhere, very separated. So the whole team had a very, very intensive brainstorm for 5 days. And there's a lot of very good ideas. And as you can see, this is just a very small part of the output of the discussion, very, very small part. I cannot show all of those. And the outcome is those 8 teams and 8 proposals. And we awarded 5 of them. As you can see, the first one is a quantum simulator. As I just mentioned, quantum computing can be used to simulate quantum mechanics. So because quantum computing is a super intensive quantum computing capability to carry on. So you can use quantum computer to simulate that. And the second one is a network, because network, there's a lot of NP-hard problem in networks research. And quantum computer is a perfect solution for combinatorial optimization. And so I don't want to go through all of them. The quantum heart is trying to resolve partial differential equation, which is also very hard if you use classical computer. And they have algorithm trying to resolve that. And there's one I want to mention. The second and last one is antibody design. It was not awarded. It's not because of the idea is bad. It's not because of other reason. I really like this one. Because the antibody design, if you have a antibody space with like 30 amino acids, each amino acid you could have 20 options. And this is like an exponential number if you want to go explore all the space. And with some of them, position is very conserved, and some of them are flexible. Quantum computer is a perfect solution trying to explore the space with flexible position. So I just want to quickly go through those 4. And Susan also briefly mentioned this one. One of these quantum computing challenge. So actually this is a program in NCAS, and our office co-sponsored this program, and it's called Qubit. And this spans quantum sensing and quantum computing together. But since our office is data science office, so only co-sponsored the quantum computing challenge one. And wow, it's changing by itself. And so, so in this challenge, we are trying to core applications to resolve, to propose quantum algorithm in drug discovery, clinical prediction, and image and genomics. And there's 2 stages. The first stage, we selected the 10, actually this first stage, the winner already been announced. We selected 10 proposals and awarded $10,000 for each one. Now the second stage, there are 2 milestones, and the milestone 1, we have been down selected from the 10 winners in stage 1 to 5. And each one will receive $150,000 to prize. because we expect them to implement them in milestone 2. You will need money to implement in real quantum computer. And the last one, the winners will be $300,000, and the second one will be 150. So this is still going on. And we received more than, I think more than 30 submissions from 50 different institutes, and already selected top 10 squad teams moved to stage 2. And as you can see, these are the 5 winners from drug discovery. So I don't think I have time to go through all of those. And the 2 from clinical prediction and the 3 in image and genomics. So all those winners has been declared in the website, in NCAS website, and the challenge website. Okay, so that's all I want to share on NIH initiatives and quantum computing.
Thank you, Fenglou. We'll have time for maybe one question, and I think then Fenglou is going to introduce the remaining speakers in this session. So let me see how I can get to you. Oh, two people here. I saw him first, and I'll come back to you.
Does there ever been a quantum simulations that has for a system that is too large to simulate with a classical computer?
You mean simulate the quantum computing programs? You don't have to. So currently, because we don't have, sorry. So since currently we don't have a real production level quantum computer, so if you have a quantum algorithm, normally you try it in quantum simulator. Like IBM, they have QSK, you can do that. But from what I know, it is pretty simple to convert your program to run a real quantum computer if you develop your algorithm in QSK. You don't have to, but since we don't have a real, very powerful quantum computer, most people start from simulator.
Hi, thank you very much for the great talk. I just have hopefully a very down-to-earth question, which is, what sort of reproducibility crisis can you foresee with the quantum fields analysis? So for example, if a research group does an analysis with 5 qubits, is it going to be different to another group that does it with 100 qubits? Is that the kind of, like, I just want to understand what sort of reproducibility crisis are we looking at with this move?
Okay, this is a very good question, but I personally is not a scientist doing real quantum computing programs, so I don't know, but I personally think it should be okay, because I say, even right now, people running quantum algorithm, they do like one sound shot. They draw probability distribution to pick. So I think if you expand to 100 qubits, it should be similar.
Excellent. Thanks again. And maybe one of our other speakers on quantum could answer that question as well. It's a really interesting one. If you have more qubits, are you going to get challenges in reproducibility? So Fenglou, you want to introduce the next speaker?